Okay, yeah, thanks for the introduction, and thanks to all organizers for putting together this very nice program. I want to talk about probing non-equilibrium topological order, and in particular, this nicely connects to a talk also given yesterday by Wenwei on Floquet topological phases, and I want to look at a particularly simple type of this order, and then show how we can probe it on a digital quantum computer. And for this, I will introduce a number of different observables to look at. And then the work has been done together with collaborators in Munich, most prominently Melissa Will, who did most of the work, and she actually ran all the quantum simulations on the chip. Bernhard Jobst, my colleague Michael Knapp, and Adam Smith from Nottingham, and the team at Google Quantum AI. But to set the stage, and I'm actually pretty quick here, is that I'm concerned looking at different phases of matter, and most conventionally we think of phases of matter at thermal equilibrium, and most of the examples that we know from our daily life, we can distinguish phases of matter in terms of spontaneous symmetry breaking. And in order to observe this, we have certain simple observables, like for water, for example, the spontaneous symmetry breaking directly relies in a rigidity of ice, which we can simply probe. So now coming closer to the topic that I actually want to talk about, I want to talk about exotic quantum phases of matter, where we have interesting phases of matter stabilized by quantum fluctuations. And most prominently, we have examples such as the fractional quantum Hall effect or quantum spin liquids. These are now systems where the ground state wave function exhibits some rather non-trivial entanglement, leading to a number of very interesting phenomena. And now this is what will be the main focus of my talk. I want to talk about systems which are periodically driven, and due to the periodic drive, exhibit some rather kind of unique features which cannot occur in equilibrium setting. So, and as I point out, like these phases of matter now cannot be characterized by symmetry breaking, but instead the things that we're looking for, or what are characterizing these phases, are directly linked to the kind of quantum order. One being that they have some non-local entanglement, and also on top of these ground states, or of the states that we find, there are excitations which can carry fractional quantum numbers, such as the fractional charges in the fractional quantum Hall, for example. And moreover, these fractionalized quasi-particles can have statistics which is different from the common bosons or fermions. So and now what I want to talk about in the following is that we want to use quantum processors for studying these phenomena. And now I want to also just stress that, or share my belief that these kind of problems, namely like studying Floquet topological order, is very well suited for this platform. And this is because the Floquet drive that we have to study is something that's extremely hard to study classically, because it just generates a lot of entanglement on the way, and so it's hard classically. On the other hand, it's fairly simple for a quantum computer because the gate complexity, so the number of gates that we need to apply, is fairly low. Right? So this is basically just proportional to the depth of the circuit that we want to consider. And this is now in contrast to ground state properties, where often ground states don't have a lot of entanglement, but yet they might be very hard to create on a quantum processor because we might need many gates. Right? So this is maybe a good probing, like a kind of playground for quantum processes. So now let me kind of discuss come to the model that I want to look at. And then now again, we had a talk about Floquet topological order, or Floquet topological phases yesterday, so I can again be fairly brief on this slide. So what we are now considering is a Hamiltonian which is driven periodically. So h of t is equal to h of t plus capital T. And because of this periodic drive, we can now look at the drive of a system for one period time, and this can now be expressed as with respect to some Floquet Hamiltonian. And the speciality or something special about the Floquet Hamiltonian is that the energy eigenvalues or the quasi-energy eigenvalues are now only defined modulo 2 pi over t. So if we have a system with periodic boundary, or if we have now a lattice system with periodic boundary conditions, we have now a torus both in momentum space and also in terms of energy space. And it's because of this topology that we can get some special type of topological phases of matter. And to illustrate this, we can, for example, if we have a system with a lattice system with periodic boundary conditions, now we can have, for example, a Chern insulator where we have a band structure of like, they say different bands here. They have 2 bands, and now these bands can have different Chern numbers. And as a result of these Chern numbers, we then have chiral edge modes. But now, if we have these Floquet topological systems, we can now also have a winding across energy space, and this is now giving rise to sort of a topological phase, or like to protected chiral edge modes with 0 Chern numbers. And this is something that would put forward by a number of papers by Kitagawa, Mark Rutner, and others a couple of years ago. And this is now the type of topology that I want to look at, but I want to look at it in not simply in a like for non-interacting fermions, but I want to look at a spin system which is suitable for simulating on quantum computers. And then I want to design a number of probes that we can use to actually test the stability of this type of topological phase on a quantum computer. So let me now start by introducing the, yes? Well, we still, like basically, so we have now a winding across the energy space, right? So because now the energy levels are only defined modulo 2 pi, and we have now a winding across the energy space. So basically this periodicity allows us to design other topological invariants which we do not have for static systems. So let me now introduce the model, and let me take some time and walk you through the model that we are looking at. So the model that we are looking at is now a driven Kitaev honeycomb model. So our starting point is now a honeycomb model where we have these crosses here now indicate the qubits on our quantum computer, and they are now connected in this on this honeycomb lattice fashion. So now we define gates ux, uy, and uz on the bonds or on the links of the honeycomb model as shown here, right? So the green ones are now ux, and a ux term is now simply given by e to the power of minus I times some prefactor times sigma x, right? So we get like some Ising x coupling on the green bonds, we get an Ising y coupling on the red bonds, and we get an Ising z coupling on the z bonds. And just recall that the kind of equilibrium Kitaev model is simply a sum of those xx, yy, and zz terms on the Kagome, on the honeycomb lattice. But now we have this driven version of this model. And also to connect this model to the Kitaev model a bit more, if we take this drive shown here and we would let this prefactor go to 0, then this is a trotterized time evolution with the Kitaev Hamiltonian. Good. So now, and this is a nice property that this drive shares with the original Kitaev model, is that all terms in the drive commute with a flux operator that we can define on each hexagon. So we just take a term which is like x, y, z. X, y, z is like the product of these 6 Pauli operators, and all terms in this drive commute with this term. So we can now define for each plaquette a Z2 flux of plus or minus 1. If we now fix the flux on all of these plaquettes, then we can actually rewrite our driving terms simply in terms of Majorana fermions. And now, if we do this, we see that each of these drive terms, like ux, uy, and uz, is now simply given in terms of like something that's quadratic in terms of the Majorana fermions. Good. And now, having this model, the option that we can now write down this model in terms of a quadratic model in terms of Majorana fermions, we can now write down its band structure. And as we now take the limit of jt going to 0, well, then we approach basically the band structure of the original Kitaev model. And for any finite jt, because of Baker-Campbell-Hausdorff, we get some perturbations which actually result in a field-like term, which opens up a gap, and it leads to stabilizing the kind of non-abelian Kitaev phase. So basically, if the lowest band here would be basically filled, then this would correspond to having the non-abelian Kitaev ground state. And as we now tune this parameter jt to larger jt, we just enter another phase, which is now the Floquet topological order, as discussed in this work by Poe et al. And the group of Ashwin Vishwanath. And this is now a phase which actually has this winding across the quasi-energy space, and it has a number of unique features which I will discuss in the following that we will use and to probe this phase or properties of this phase on the quantum computer. This is now at the level of a non-interacting model. Once you kind of, it's a bit hidden because you have to do this transformation, but then it becomes a model which is quadratic in terms of Majorana fermions. But then we now add another period of this drive, like a fourth period in this drive, where we have now a disordered field. And what this disordered field does is twofold. On the one hand, adding this disordered field that we're going to apply, it breaks the integrability, so it actually adds interactions to the Majorana fermions, on the one hand, and on the other hand, by adding this disorder, it also allows to localize or to many-body localize the system to prevent it from heating. And now, on the machine, we will go and try to study the effect of this and trying, at least at a pre-thermal sense, trying to understand the stability of the phase. Good. So that's the model. Are there other questions about the model? The setup? Good. So now we can come back to the simulation of this on the quantum computer. Yes? Well, the topological order is meant to be robust, and the danger that we have is a heating. So we want to prevent the system to heat. So you can say, like, if we just do the drive and we add interactions between the particles, then it will just heat. Like let's say that we just take this model and we just add like a staggered field or anything.
So what I have in mind is
well, the thing is that because basically we have in the original model, we have like these static fluxes that are fixed. The moment that I add like some arbitrary spin terms, what's going to happen that these fluxes these terms will generically not commute with the flux terms. So they will just get some kinetic energy and start to heat up everything. But basically, the reason why we choose these disordered fields is now that, well, the fluxes will get some, they will no longer be perfectly localized, but if they are would be many-body localized, the whole thing would still go through. I think that this is the rationale behind it. Although, I mean, since we all have doubts of many-body localization in 2D, this is eventually going to heat up, but the hope is that there's now a finite, like a long enough range of time such that we can actually observe signals of this this phase without the system actually heating up. Yes? Well, I mean, it adds, right? I mean, basically what it, like, let's say that we just take the original model and we just add now some local field terms. What this will does, this is what actually kills the story, is that it now, the fluxes are no longer conserved, so basically the fluxes get some dynamics. And this is what I want to prevent. And if I just have a disordered on-site field, that's sufficient to localize the fluxes, at least at a pre-thermal sense. Good, right? So, but let's just stay actually fine-tuned for a while. That makes also it easier to think about. So now basically what we first have to do on the quantum computer is that, well, the quantum computer is now initiated just in a very simple state. This would be just a polarized state where all qubits are, say, in a zero state. And now we can devise a gate sequence, which is actually very similar to the gate sequence. It's just reformulating the gate sequence that you use for creating the ground state of the toric code model. So if you just now apply this gate sequence, which has a depth which is scaling linear with the linear system size, then you end up in a state where the expectation value of each flux operator is +1. And we can now choose a state such that the pairing of the Majoranas is now just between nearest neighbors, as shown here. Right? So basically all these purple lines are now two Majoranas pairing up to a complex fermion, which we just choose to be empty. Right? So each of these complex fermions can, of course, be occupied or empty, and we just choose now a state that each of those is now in a state which is not occupied. Right? So now we have a gate sequence that we apply to the machine, and then we are ending up exactly at this state. And the nice thing is, if we have this picture, and we just arrived here, we can in principle completely forget about our starting point that we had a spin model to start with. We can now just literally just think of this as a model acting on these paired Majorana fermions. And this helps us a lot to understand what's going on. Because now we can just revisit our drive term. And for a moment, I want to fine-tune the amplitude here, this jt, to be equal to 1. And in this case, the terms here are very simple. In particular, we can now take a single plaquette, as shown here, right? So the background color means that the flux here is +1, and now we have the Majorana fermions paired in this way. And if I now act, say, with the UX drive, but equivalently with any other of these drive terms, it actually corresponds simply to a Majorana swap, right? So basically, if I now take that configuration, it just swaps the two Majoranas. So now we basically have these two Majoranas paired to a complex fermion that's empty, and these two. So now we can actually have a very clear picture of what this drive is doing. Now we can start playing with this. Now I want to first show the first results that we actually obtain on the quantum computer. So now what we do is we just run our initial state preparation protocol where the Majorana fermions are paired in a certain way. And now, of course, all the Majoranas are paired with someone else, but just to have a less messy plot, we just highlight only the occupancy of two of them. And now the numbers that you see are the values measured on the machine after preparing the state. So we measure that instead of a 1, which we wanted to have, we would like to have each of these plaquettes to be in a state with flux 1, with probability 1, but we have it with a probability of the order of 80% or so. So basically in practice, what it means, like later on, we're going to do post-selection, which means that we can just take about 80% or so of our shots. And then we also measure the probability of finding the fermions here in the empty state. And again, this is of the order of 80%. And then the other fermions we are not showing here for clarity. But now we can apply the drive. So this is basically what we got right after the state preparation. And now we just apply the drive, right? So this is from here to here, we have u, x, y. U, x, u, y, u, z. And then u, x, u, y, u, z, and we get here. And there's now the following thing that we observe. So first of all, the Majorana mode that's in the bulk, it's actually localized. So it just flip-flops between these two modes. So this is always localized on this plaquette. However, Majoranas that we have sitting at the edge, they are now moving around in this chiral fashion around our open boundary. And this is now one of the hallmarks of this phase, so that we have particles in the bulk being localized and particles at the edge following this chiral motion. Yes? Well, at this point, here it's just a game we play because it's actually exact. So at the jt equals to 1, we can actually just, we wouldn't need to use a quantum computer, we can just draw it on a piece of paper because we actually know, and that's why I said this is a nice playground to start, because now at jt equals to 1, each of these operators is exactly a Majorana swap operator. So all that is doing is this, we can just exactly draw what we should get if the quantum computer is perfect. And we see that, well, it's not quite perfect. We see like that there's a decay of our probabilities to measure it actually in the right state. And the signal, or the signature is now that we have these kind of chiral edge modes, which again, we can here just draw with on a piece of paper. Just by taking literally this kind of Majorana swap operation. Good. So, but now, kind of continuing with this game, we can now do the following. And now we can already kind of still stay at the fine-tuned case, but measure something which we just which is like it is showing that the quantum computer is doing something right. So now let me first describe the protocol that we're using, and then say a little bit about the physics. So the protocol that we are running is now shown here on the top of the slide. So first we have now our box here to initiate the initial state. And this is now a protocol which gets us this state here. So all the plaquettes are in the +1 state. There are a bunch of locally paired Majoranas, which I'm not showing here, but we are now preparing a Majorana such that it actually spans across the system. So this is maybe a non-local fermion, right? So these two Majoranas, one being localized here, the other one being up here, form together now a complex fermion mode, which can now be occupied or empty. Good. So this is now done by this box. And now we have another qubit, which is our ancillary qubit. And on this, we just first apply a Hadamard gate, which means we just take the state which is in a 0 state, we bring it to a 0 + 1 state, and then we apply the control operation. So we basically, in that copy where this bin is down, we don't do anything. In the other one, we are applying here an X operation, which means, translating it back to the language of the Majorana fermions, we're actually now creating a superposition of two states where this Majorana is occupied and where this Majorana fermion is empty. And then on the system, we're acting with our gate sequence, which is now applying ux, uy, uz, ux, uy, uz. And then after this, we are just now applying another control X operation, again on this qubit, and then we're just measuring this qubit. And if we now measure on this ancillary qubits, what we actually measure is now shown here. So we just now take the state which is where the fermionic mode is empty, we just apply our gate sequence n times, then we just act on it with the X operator, which means we change the occupancy from occupied to empty, or from empty to occupied, and then we overlap it with the occupied mode, which also has followed the same gate sequence. And then we just again know exactly what to expect, because basically, if you take these Majorana, you just rotate it by 180 degrees, we should pick up a phase of e to the I pi of pi over 4 with a sign plus or minus for occupied or empty fermions. So the relative phase that we should get after braiding these Majorana fermions should be e to the I pi half. Right? So we get something very specific to look for if these defects correctly resemble Majorana fermions. And now this we can now do on the quantum computer. So we now first do this preparation step and then just do the measurement. We see here that with an amplitude of about 1, like this has the amplitude about 1 and a phase 0. And now we just can go on, and this is now shown in this movie. So now on the left-hand side, it shows what we know is going to happen just by drawing with a piece of paper, just by applying sequentially these kind of swap operation. And here we now see the overlaps. And then, well, as in the intermediate steps, we just measure basically 0. This is because this X operator is basically just creating an orthogonal state. And after a full period, we then measure a finite, like something finite, which should be 1 if the quantum computer were perfect. But if it's since it's not perfect, it's smaller than 1. In fact, it's kind of exponentially decaying here. And then we can also extract the phase factor. And the phase factor we see indeed after 5 periods, which is like the number of steps which we need for actually doing a full 180 degree rotation. We just pick up a phase of e to the I pi half, and then another one after 10, another one after 15, and so on. So this spirals in, but in a perfect quantum computer, which just kind of go across this this square. Right? So basically, using this kind of fine-tuned model, we see that here we can actually kind of simulate the braiding of non-abelian anyons in using this protocol. Good. So both these examples were now done for the highly fine-tuned model of JT equals to 1, where the system is now like where the terms simply correspond to Majorana swap operators. But now we can also detune it, and we expect that certain things should be stable even if we detune, if we just go away from these fixed point states. And one thing that we then thought about measuring is actually the kind of Majorana edge spectrum. So what we do for this is we are now looking at the unequal time or the dynamical correlation function of Majoranas at the edge. Right, so we are looking, we want to now measure correlation function Cjn, which is now the correlation function for basically acting with a Majorana operator at kind of site 0, at time 0, and then we just correlate it with applying this operator at site j, somewhere else on the edge, at time n. Right? So we measure discrete times in terms of the number of times we applied the gate sequence. And this again, we can now, this unequal time correlation function, we can now again measure this Hadamard test, the one that we used also for the interferometry before. So we now have our gate, like so we have now our gate sequence that we need for prepare the initial state. We just apply the Hadamard gate, and now we just apply a control operation, which is now creating a Majorana fermion here in the system, and then we just drive the system, and that would just lead for this chiral Majorana fermion to just move in this chiral way, and then we can now do the measurement on this ancillary qubit, and this is then exactly measuring our correlation function as shown here. Now we can measure this system and Fourier transform it to then get our chiral, like to get the spectrum. And what we see is that, well, at the fine-tuned case, we see now a perfect kind of chiral mode. Like here's like the energy, and here's the momentum, and here you have like this now winding around energy space. So this is exactly this picture here. And if we now detune, we see that, well, for a certain range of parameters, this chiral mode actually remains robust until we leave the phase, like maybe at JT 6 or 7, we're just leaving the phase. And then we see that the chiral edge mode actually dissolves and turns eventually into some quadratic dispersion. And we also can add the disorder term, which again doesn't stop this chiral edge mode, not on the energy resolution that we see here. Right, so basically now this is the first example where we look at a case where we tune away from this fine-tuned case, and we see that there are some signals, at least on certain time and energy scales, where these kind of topological property or the properties of seeing these chiral edge modes is actually robust. Now, I want to look at a bulk invariant, and this is the last thing I actually want to talk about here. Is now we want to have a quantity which we can directly measure in the bulk, so that it does not rely on having a finite boundary or like having open boundary conditions. And the protocol that we look at is now the following. So again, we now take our system here, and we now have a sequence, a gate sequence that we can apply for preparing each plaquette in the +1 state, like we are going to the flux-free state, and we pair the Majoranas in a very local way, as shown here. Then we do the following. Now we just take our state that we created, and we act on it with a string operator going from the inside here to the outside. And well, if you have a system actually with no boundaries, we just have the other end just far enough away. But here we have still open boundary conditions, so we can actually just throw it outside of the system. And then what we are left with is that there's a single plaquette in the middle where we actually have a flux which is -1. So this is now the gray plaquette where we have a flux of -1. And moreover, what we do is we now change the occupancy, or like the way that we prepared the state. This fermionic mode spanned by these two Majorana fermions is now occupied, as opposed to the others which are all empty. So what we have in the center is now a magnetic flux plus a fermion, and the kind of molecule of those two together is actually now an E anion. It's like the same type of anion that you would find in the toric code. Right? So this is the type of excitation that you also have in a toric code topological order. But now we have the following. Again, let's first discuss it for the fine-tuned case. If we now apply one gate sequence, like if we just now apply this now for one drive period, what this will actually amount to is to have these Majoranas to move around our flux excitation, and by this, they will actually change the occupancy of the fermion from being occupied to being empty. Now, that means that after one drive, we're actually turning this E particle, which is actually the bound state, or like the molecule of a flux excitation plus a fermion, to just having only this flux excitation, which is now the M anion. Again, using the same notation that's used for anions in the toric code. And then if we just do now another drive, this fermion will again go back to the occupied state, and then we just turn the M again into an E. So basically what we have is now a transmutation of an E particle to an M particle to an E particle to an M particle after each drive period. And now we can use this to design an order parameter. So basically what we do now is that we take an operator, which is like a Wilson loop operator, that is now encircling our defect, our isolated defect that we have here in the center. And of course, we can make this loop as large as we want to it, as large as our system is. And this will now be sensitive to what type of excitation we have in it. Right? So for example, if this is now the Wilson loop operator for our magnetic excitation, then it will actually be +1 if we have an E excitation in it, and a -1 if we have an M excitation in it. So basically, if we now, for this fine-tuned case, measure our Wilson loop operator, it will actually flip-flop between plus and minus 1 after each drive period. If, however, we are tuning away from the fixed point, then this Wilson loop operator will not be the exact Wilson loop operator, and instead of measuring something that's flip-flopping between plus and minus 1, we would actually have something that will decay exponentially with the length of the string. So then we would not have any signal left after a while, or for sufficiently large systems. And what we are then doing, and this is sort of motivated by what's also done for the Fredenhagen-Marcoux order parameter, which is a bit similar in spirit. We now basically divide this by another quantity where we just don't put anything inside. Right? So if we just measure the expectation value of this Wilson loop operator where we just have no defect inside, we would expect that, well, this is just constant 1 in the exact case, but if we just detune it, it's something that will decay exponentially, but it would not have any phase oscillation, but it would have the same decay as the one that has the phase modulation. And as long as the defect is sufficiently far away from this defect line, they should decay in exactly the same way. And then that's why we can now just compensate for this exponential decay. Good. I mean, just a lot of talking, but let me just quickly summarize. So we have basically now this kind of non-local order parameter, which we expect to flip-flop between plus and minus 1 in the this Floquet topologically ordered phase. And this is now indeed what we measure. So this is now this JT, which we can now tune, and for 1, 0.9, and 0.8, we see this nicely flip-flops between plus and minus 1. And if you just kind of go into the, if you just make JT sufficiently small, then we just enter the other phase, and you see that this actually just shows no oscillations. And now we can actually just take this together and design an order parameter from it. So we now just do a Fourier transform of this signal, and then, well, in the fractionally in the Floquet topologically ordered phase, we would then have a peak at pi, and in the Kitaya phase, it would be a peak centered around 0, and then we can now here just design an order parameter, which is now where we just take the difference of the signal, the absolute value of the difference of the signal at pi and 0, such that this number is then kind of distinguishing the two phases. And now this is just shown in this plot. This is positive for the FTO phase and negative for the Kitaya phase. And then we see that with this order parameter, we can now nicely map out the phase diagram. And note that this is now actually done on the machine with 58 qubits. And we also tried to do this with DMRG. And while we just we get a similar phase diagram from DMRG, but there's already kind of significant amount of truncation, and the error of the DMRG is actually larger than the error that we get from the actual data on the machine. But let me conclude here, mainly by just saying that, well, we just probe now various features of Floquet topological order, and let me acknowledge my collaborators and highlight really Melissa and Bernhard, who did really the heavy lifting on this project, and my colleagues Michael Knapp, Adam Smith, and the team at Google Quantum AI. So thank you for your attention.